It's my genuine pleasure to introduce Lennart Persson. Today, Lennart is a native of Lund, where he did his bachelor's and PhD once upon a time, and as well did a equivalent to forskarassistent, so junior researcher type of position, kind of like what I'm doing now down in Lund. And since 1987, Lennart has been a member of the ecology department here in Umeå, where he conducts his work, where he looks at the importance of intraspecific size variation and the impact that this has on population and community dynamics. So I'm interested in learning more about his work because Lennart's told me that he tries to combine empirical work with theory, so it's Persson after my own heart. Lennart has authored over 130 papers, making him, earning him rankings as one of the most highly cited scientists in ecology according to the Web of Science. I think about a dozen doctorand have graduated with Lennart in that area. Also, among his other achievements, he's a fellow of the Royal Academy of Sciences here in Sweden. He spent 9 years as chair of the Ecology and Systematic section of VR, so I know who I can go and talk to improve my proposal in the spring. And he's also an assistant editor of Animal Ecology. So without further ado, I'll turn the floor over to Lennart.
Oh, thank you very much, Stace, for this very nice presentation, short. So, what I'm going to talk today about here, you have a title, Symmetry Breaking in Ecological Systems Through Different Energetic Efficiencies of Units and Orders. A new paradigm unfolds. This is something that I've been working on for 20 years together with André Duros at Amsterdam University. So this is kind of, I would say, the first synthetic part of 20 years of research, where we now are at the stage where we can present a more synthetic theory. So to start with, I will just give a couple of fundamental statements. And the first fundamental statement is ontogenetic development characterizes the life history of all organisms in the world. And this is of course obvious because if you look at different taxa, we know that among animals more than 85% of them undergoes metamorphosis. So we have quite a bit of ontogenetic development. Even if you look just at vertebrates, due to the dominance of fish, amphibians and reptiles, still the majority of organisms has a substantial juvenile period. But more than that, even if we would go to something very extreme, a unicellular organism like a phytoplankton and bacteria, even that has a life cycle through the cell cycle, where when the cell divides into 2, 3, 4 daughter cells, it sets up a life cycle for that organism too. So I think this is a pretty fundamental statement that is true. The second statement is kind of another strong statement, and that I just quote here, that ontogenetic development is not comparable to any other complicating factors like interspecific genetic variation, stochastic variation, or spatial heterogeneity, how important they are. It's not something that can be added to a core ecological theory. It is instead essential. Development is, as reproduction and mortality, an essential component of population dynamics that can never be excluded and whose impact can never be eliminated. That means without development, in addition to mortality and reproduction, there is simply no population dynamics. Strong statement. And I would say without development, we don't even have a full characterization of the individual. Two fundamental statements. So now comes the problem. If we look at standard ecological theory, ignores ontogenetic development altogether, as it defines then population dynamics in terms of changes in the number of individuals only. Major problem. For I would say most ecologists, we have another problem, and that is that they fear that incorporating ontogenetic development leads to an overwhelming complexity with limited possibility for generality. I think that's a view held by many ecologists, the second statement. And I will actually try to convince you here that this is certainly not true. So, with these two problems still, what is the way ahead? How to go ahead? Well, what I would do here is actually develop an ecological theory based then on symmetry breaking, considering three processes: development, mortality, and reproduction. And for those who don't know, we should know that mortality and reproduction is viewed as two major regulatory mechanisms in population ecology. Onto genetic development, not yet. And I will advance then onto genetic asymmetry and symmetry in individual genetics as fundamental concepts to ecology. And this leads actually to novel and synthetic ecological theories for population communities where present contemporary unstructured theory actually falls out as a very special limiting case of ontogenetic symmetry. So, now I already mentioned the word symmetry and asymmetry. Well, what do we mean with that? I missed this. Actually, this also provides us a linked individual-based model hierarchy that I will not talk about today. So, if we consider then, a consumer life cycle with consisting of juveniles and adults feeding on a resource and having mortalities, their maintenance, both stages. This is kind of what unstructured theory is doing. They said that actually the mortality is a regulatory factor for both stages, and resource level will determine actually the reproduction. So reproduction is then food dependent. But if we now add upon this ontogenetic development and makes food dependent the maturation rate food dependent, then instead of only then having this regulatory mechanism here, we get two: maturation versus reproduction. And that opens up then that we get two potential regulatory transitions in the life cycles. And which of these two processes that is limiting relates then very much to whether you have symmetry or asymmetry. Simply spoken, I will show you more detail and formal about this. You can state that actually you have symmetry when the rate of reproduction actually is similar to the rate of maturation. But in all other cases actually you have asymmetry. So how can we define then ontogenetic symmetry? Well, I've used here the Yotsis-Innes model, which is a biomass model where the units of biomass is actually the units that is measured. And this equation is actually pretty simple in a sense that this is basically the function response or the biomass ingestion of an individual as a function of resource levels, and we see two parameters here, the half saturation constant and the maximum ingestion rate. So this is kind of a type 2 function response. The important aspect of this model is that actually biomass consumption is expressed not per unit of individual, but per unit of biomass. Then we have the other aspect, that is the net biomass production, which is just then the intake times the conversion efficiency here, sigma, minus metabolic demands. So for that actually we have then describes the net production of new biomass in the population. And the equation system then for a consumer resource system is here consists then of a resource with an intrinsic growth rate function, which we have not defined here, we don't need to that, minus then the death rate in terms of biomass through consumption of the consumer. And the dynamics of a consumer in terms of biomass is then its net production that we had here, minus the death rate of this the consumer population. What do I mean that this represents a case with ontogenetic symmetry? Well, that relates to that consumption, consumer ingestion and net production, these two terms of new consumer biomass, both in this equation system scale linear over body size. That is, intake and production is constant per unit of biomass. We also assume that this conversion of food into new biomass through somatic growth and into reproduction that they are equally efficient. And finally, we assume that mortality rate of a consumer is independent of body size. This is then what can be defined in this modeling terminology as ontogenetic symmetry. The interesting thing with this model is that it has a dualistic nature. Why? Okay. Because under equilibrium conditions, it is an exact description of a biomass dynamics of a fully size-structured model that takes into account very explicitly an ontogenetic development under the condition that we have ontogenetic symmetry. So we can take a fully complex size-structured model, and it can be shown then that under equilibrium conditions, that model can be reduced to this model. So this is not basically this biomass model is, although it appears as an unstructured model, it is not an unstructured model. It's the simplest scenario of a structured model for ontogenetic symmetry. The nice thing with it is it still has the dynamical properties of unstructured model. I mean, it has aspects like consumer resource cycle, paradox, and enrichment. So actually, it has both elements then of a fullest size-structured theory for a special case, but also can be used as an approximation of unstructured models. So this is then ontogenetic symmetry, and that holds for all unstructured models. So ontogenetic symmetry, to define that, I mean, we do the simplest thing I would do here. I separate up the population explicitly into juveniles and adults. Juveniles, they grow and mature. Adults only reproduce. We set up the same type of equation for biomass ingestion and biomass production, and you see the same equations. But we are now separated up the biomass ingestion of juveniles and adults here, and the net production of biomass in juveniles and adults. And if we compare actually the equations for the juveniles and adults, we see that they differ in only one parameter, this parameter Q. You can see that the ingestion here is multiplied by Q for adults and by 2 minus Q for the juveniles. We do a similar thing with respect to mortality. So we have this P here, which you multiply for adult death rate with a basic mortality rate, and for juveniles is 2 minus P. And what we can see here is that we can, in this system, actually show exactly what we mean with symmetry. With symmetry, I mean here that Q equals 1, because if we go up here, then actually we ingest per unit of biomass ingestion and production of juveniles are the same. It's also, given that P equals 1, because then the mortality rates of juveniles are the same. So for Q equals 1 and P equals 1, we have symmetry. But for all other conditions, we have asymmetry. So that is basically a simple way of using this stage-based approach to actually explain what is ontogenetic symmetry and ontogenetic symmetry. Now the population equations becomes a bit more complex, but not that much. We can see we have a growth of a resource minus a consumption of juveniles and adults separated here. We assume that adults only reproduced, and that means that the net production of adults goes into juveniles directly. Right? Then also the juveniles are growing with this equation. The second here, they mature into adults, which is this equation, minus, and of course it appears as a plus in this in the adult equation. And then we also have the separated juvenile death rate and adult death rate here. And nicely enough, this equation system, if we set actually then the net production of adults to juveniles to the same and the death rates the same, actually this equation system can easily then be actually collapsed into the Jotsons and Ians model. And of course, this is another way of stating that under this condition we then have ontogenetic symmetry. Now I used a stage-based formulation here just to illustrate what I mean with asymmetry, asymmetry and symmetry. But actually a recent paper, it will appear next year in Journal of Mathematical Biology, which is a more mathematical treating that where it's mathematically proven that any size structure population model which is characterized by mass-specific population invariance and mortality invariance can be reduced to a single ordinary differential equation for total biomass. And in this case, total population biomass dynamics decouples from the dynamics of a relative population structure. So relative population structure is invariant to changes in environmental conditions, which is not then the case for ontogenetic asymmetry. But at the same time, this paper once again says that a theory based on unstructured model only applies to conditions of ontogenetic symmetry. So much. Now I define what is ontogenetic asymmetry and symmetry. What are the implications? Are there any? Well, I will have consider 3 of them. The first is a basic, and that's what I call overcompensation. What do we mean by overcompensation? Well, if we look first on this graph in the middle, where we have consumer biomass on this axis, and this is mortality that is random, it's a mortality that is affects both juveniles and adults. This is the biomass of adults, this is the biomass of juveniles, and how these biomasses respond then to increased mortality. And what we see is what we know from standard ecological theory. Consumer biomass decreases with increasing mortality. Up here, there are 2 panels showing actually the stage distribution of juveniles and adults at low mortality and at high mortality. And actually then also their maturation and reproduction rates relative, the resource level, and we can see that imposing mortality leads to higher resource levels, which leads, but we see that at the same time that the relative ratio of juveniles to adults doesn't change. So this is kind of a standard here. If we now introduce a case where we keep now the mortality the same for juveniles and adults, but we introduce a symmetry Q smaller than 1, and that means that juveniles are better competitors in the system. Something very different happens because now, once again, adult biomass decreases with mortality, but juvenile biomass goes up, follows a hump, so first increases to where take a level off. And in the same way we see here, as for this case, we see actually then changes in the biomass distributions of with respect to juveniles and adults, such at low mortality. Then actually we know that the juveniles are better competitors. Adults are heavily limited by the low resource level. And most of our intake is actually lost through this arrow here, which is actual maintenance cost. There is no other mortality, but you can see that most of what is going into the adults is lost in maintenance. We see also that juveniles are better competitors, so that they have a higher rate of maturation. So lots of the juveniles moving to the adult stage get stuck there, low fecundity and low reproduction rate, and we get few juveniles. So in this situation, we have the heavy dominance of adults in the population when juveniles are better competitors. If we now increase mortality, and this is a random mortality, what we basically do is that we actually release adults from competition by reducing this rate, the number of individuals going into the adult stage, but also by taking away adults. This actually leads to a substantial degree in the cost of the maintenance cost hut, and we get an overcompensatory increase in adult reproduction rate like that, which leads to higher juvenile biomass. So despite juveniles, maturation rate goes up, but they are less resource limited, so they are not going up as much as population reproduction rate goes up. So we get more juveniles here, and that's the explanation for this hump here. In the case when it's the opposite case, Q is larger than 1, then orders are better. And then you get for the same argument exactly the opposite pattern. Juveniles decreases in mortality monotonically. Orders shows a hump. We have most of the biomass in juveniles, high reproduction rate, low maturation rate. Imposing mortality then leads to actually a release of juveniles here, and then maturation rate goes up. And that is then the reason that why we get this hump-shaped response. Experimental evidence. This is a study by Arne Schröder, for most of you know, that actually carried out this experiment on released killifish, actually showing then that in this case he actually in one treatment actually increased just juvenile mortality or adult mortality. And if he increased adult mortality, he showed typically this hump in response of the juveniles. But that was even present, significantly present, even if these juveniles were exposed very much for mortality, you still had this hump that is overcompensation in biomass. In adults, not or even a decrease. There are, a number of other examples. This is 2 examples. One is then a system that is then limited by reproduction, which is the Windermere perch. So this is the biomass response of the juveniles to mortality actually. We see that increased mortality has led to an increase, whereas the opposite holds for adults. Increased mortality leads to decrease in biomass. So we then have a state-specific overcompensation in the juveniles here. This is from a soil mite study, Cameron and Benton. Mr. Cameron is here, Tom's sitting here. And here we see that a slight decrease in the juveniles, but then an overcompensation in biomass of the adults. So this is then a system that is then limited more seemingly from maturation limitation. So, overcompensation is an important element. You can show it in theory. There is an increasing number of experimental studies showing the presence then of these state-specific overcompensation patterns. So, part 2 then, what are the community effects of then ontogenetic asymmetry? That is actually coupled to what we just saw, overcompensation. I will just use 2 examples here to show what can happen. And the first one is kind of the most classical one, and that's something we call emergent alley effect. And this shows a system with a consumer and a resource that is then reproduction limited. And then we know that you have a dominance of adults, but low reproduction rate, lower biomass of juveniles, but the high maturation rate here. And this emergent alley effect, it's actually related to that such a system actually can show actually 2 alternative stable equilibria. Because if we look at this system and we imagine a predator feeding on the juveniles, we have here very few juveniles biomass in this system. So the predator may not be able to invade this system. However, if a predator like in this figure here is in the system, it is actually thinning out the juveniles, it's eating the juveniles. But that's lead then to actually through actually that orders are released from competition to an increased reproduction rate. That is, predation by the predator on the juveniles lead to an increase in the biomass of the juveniles. So we have then 2 alternative stable states, one with only the consumer resource and one with predator consumer the resource. And an experimental example of this is when this study of the brown trout system in Lake Tagvatn in Norway, where the population before this experiment was totally dominated by small-sized char. And actually there were no trout in the system. What the Norwegian was here, that they removed enormous amounts of the char, the prey of the brown trout here. And what did this mean in terms of overcompensation? If it's true, yeah, what they do is basically they impose by fishing a mortality of on the char system. That if this is a reproduction limited system, that actually releases adult fecundity, which actually can lead to an increase in the biomass of juvenile small Arctic char. And we see what happened in this system. This is just condensed figure. What we see here is that before this experiment, we had very high abundance of a stunted population of char. You had a 5-year period of heavy fishing, reducing the char, and since then it has been fluctuating towards a new equilibrium, kind of. But the important point was, following this fishing, actually the predator actually re-established itself in the system and has actually been at high density for more than 20 years. We can look whether this is a result of a mechanism I proposed here, the Merger-Dell effect, by looking at, this is a fully size tracking model which shows the size distribution of the consumer here, the Arctic char, in the absence, the gray bars here, in the absence of a predator. And then we see that they don't get very large because, and that is well known because competition is so high. Whereas in the presence of predator, the predator finals the population, you get more of the big ones. But the important thing is you also get more of the small ones that the predator is feeding on through increased population fecundity here. So I mean, even though this has been well known before, and it's this aspect is an important thing. It's actually this that then leads to these emergent early effects, that the predator's activities increases the prey densities of its own prey. And this is actual data. It's not in the same units. Here it's abundance capture per unit effect. But we can see the same thing before the thinning was totally dominated char by individuals between 15 and 20 centimeters. And in this case, we know that most of the brown trout do not feed on char larger than 15 centimeters. We see that after the thinning, lots of large ones, but more importantly, we actually get an increase in the small Arctic char. So this, despite that the brown trout is preying on these ones, it produces more of it. A major ecological effect. The other examples I will use is kind of different, and I would just show you here the model effect. And that is that an increase of the resource of your prey may lead to your extinction of a predator. And that is shown in this figure. Because if you, in this case, the controlling variable is the resource productivity of the juveniles. And here we assume that adults and juvenile consumer, they don't share resources. Adults feed on one resource and juveniles on the other resource, which is actually quite common. So, what happens now if we increase the resource productivity in a system with a system where the predator is in the system and feeding on the juveniles? Well, it's sketched here that this leads to, you increase the resource of the prey, that leads to the predator extinction. And why is this happening? Well, what you do here is basically you give more resources to the juvenile, you speeds up maturation rate, but the resource productivity of the adult hasn't changed. So you trap the adults in a bottleneck, and reproduction rate goes down very much, and you get less juveniles. So basically, in this case, the increase in productivity leads to the extinction of the predator. And over a productivity gradient, you can go then from this system to alternative stable state to consumer resource only situation. So the major conclusions here when focus on community is that when ontogenetic asymmetry and overcompensation can lead then to alternative stable state through state-specific overcompensation and biomass redistribution. I mean, I used just two examples, and they differ in one aspect, because the first example related to different actually ingesting scalings of small and big Arctic char. The other one, actually what was changed there was the state-specific resource production. So that was extrinsic actually to the individual organism, which already here points to that you may induce ontogenetic asymmetry through actually extrinsic factors do. Just two simple scenarios, but actually this can be shown then to carry over to more complex situations with ontogenetic niches, including, for example, interspecific competition, mixed competition, predation interactions, and so forth. And here are just some examples of papers who are dealing with that. So then ontogenetic symmetry has major effects then on community structure that is not present in unstructured model. Does this effect carry over to population dynamics, and can this be explained by the same process of actually asymmetry in maturation versus reproduction rate? Can that be carried out to when we study population dynamics? The answer is yes. And for this actually, I will actually use, or this is based then on a fully sized structure model with a size distribution of individuals that actually from a certain size they are reproduced, they are also exposed to mortality, and they all feed on a resource here, but with different efficiencies. So for this, we basically used explicitly a chemochemostat resource dynamics. And the reason for that here is to look specifically at the effect of ontogenetic symmetry through this cube, because we know that under ontogenetic symmetry, unstructured model, with such a resource growth, we will not exhibit any cycles, because we know that predatory-prey cycles are depending both on a type 2 functional response and logistic growth equation. And surely enough, if we look at Q around here, this shows then the maximum and minimum biomass of juveniles and the maximum biomass and minimum of adults. We see that we have no variation here. So that's true. For ontogenetic symmetry, no cycles. But as soon as we get ontogenetic asymmetry, actually, we get new type of cycles that are not classical predatory cycles, which we call them generation or Koch's quartz cycles. Here is an example of a time series for when juveniles are more efficient. And then we get what we call juvenile-driven cohort cycles. And we can just follow here a reproduction pulse that gives rise then to a juvenile cohort. And actually this juvenile cohort, it dominates the system. It's very efficient in feeding, and it actually suppresses the fecundity of the orders in the population. So we just have a pulse of reproduction, then reproduction goes down to zero. And this cohort then grows in biomass and gives rise then next to another pulse. If we have Q larger than 1 here, we also get cycles, but they look differently because as for community structure, in this case, orders are more superior. So we can see first that actually we have a reproduction going on, it varies, but you have reproduction present all the time. So they are quite different. And in this case, it was a strong cohort of juveniles that dominated the system. Here you get, as we will see in the next figure, a stacking of juveniles because you have a huge competition by among juvenile cohorts through actually this reproductive output from orders. So in this case, orders threw in to the juveniles, they all the time to more or less the same new offspring that actually slows down the development of juveniles. And that, among other things, leads to that the time scale here is much longer than in the other case. And what we can see here is that exactly the same as for community structure, that when juveniles are better competitors, orders dominate in biomass. When orders are better competitors, juveniles dominate in biomass. And this is then typical system limited then by maturation, limited by here by reproduction. And you can go through detail after detail and see that these cycles can be totally explained by actually what we know about ontogenetic asymmetry, etc. So just two experimental examples. This is a case when from a yellow perch system in Wisconsin, where then Q is equal to 1, and this shows then time series at 3 different times in the model. We can see this strong cohort that is born here. These are the adults that actually then grows over time. Importantly, we see nothing coming here because this cohort depresses the resource and prevents any new reproduction. And these are the empirical data showing, and actually here is a strong cohort born, but it's not shown in this graph because the trapping gears didn't trap this size class efficiently. But we can see it the next year here, this cohort coming and that grows and matures. And we can also see that actually in this case, this strong cohort kills off all the others. So basically actually the strong competitors of these juveniles actually drive all the others to starvation mortality. The other case is interesting because that's a case when Q is larger than 1, and I will explain more later. And this is actually a unicellular organism this is a chlorella system. And in this system, we have this, we can see that we have reproduction going on all the time because we all the time get new juveniles coming into the system. But they are kind of stacked, very slowly moving, and eventually they may move then into the ordered stage and then give rise to new juveniles. And this study by Massitais on the chlorella actually showed this type of cycle that you can see here actually this movement of many cohorts then approaching ordered stages. And the ordered stages is here actually then the stage that is actually just about to divide into new daughter cells. The mechanism proposed in this case is that the pre-mitotic stage, the sizes of then this chlorella that are not dividing, they have in this experiment was heavily limited by nitrogen, whereas the mitotic state was not limited at all. So I mean they all once they were about to then divide, that rate was not really affected by low nitrogen levels. And in this case actually each major cells actually gave rise to 4 new daughter cells. So even in this unicellular system you have these cycles. And it's a big problem, I would say, because there is huge literature on cohort cycles in biotechnology related to wine production. Because in wine production you want to keep environmental resource level constant to get a good wine. So this actually set up the system for chemostat resource dynamics. The problem is that they still get cycles. And these cycles, which are these cycles, they destroy the quality of the wine. So it's a major, major practical problem, these cohorts, in this sense. So, but nevertheless, I mean, just to say that these have been observed and there's a rich literature on it. I talked now about 2 types of cycles, one where the juveniles are superior and one where the orders are superior. The question is, how common are they then related to actually what we learn from textbooks, predator-prey equation? Well, this is a review in Nature by Murdoch and al., and I think we should just concentrate on this figure that showed from a huge data set they used on population dynamics. They separated out the number of populations showing then single generation cycles. That is the cycle I talked about here, cohort cycles, delayed feedback cycle, which is another cycle related actually to ontogenetic symmetry. And this is then what we call consumer resource cycles, and these are predator-prey cycles. And this actually analysis of empirical data shows that these 2 types of cycles together are substantially more common than predator-prey cycles that totally dominate our thinking. I already mentioned when I discussed this community effects of ontogenetic symmetry that you can actually induce ontogenetic symmetry both by intrinsic and extrinsic factors. I mean, what I mean here with intrinsic was basically that we were here varied Q. That is, if Q is not equal to 1, we have ontogenetic symmetry. And that is a characteristic that relates to the individual. Some may have noted that we didn't do this with a maintenance rate and maximum ingestion rate, but we could very well have done that. So you could also have, because these 2 parameters, they were still symmetric per unit of biomass. So you can actually have a symmetry in these 2. And another aspect here, and these are of course also related to the individual. The final thing is the birth to maturation size, which I have called the Z, which we can think about, may be important in this context because it affects the time delay. Because the smaller this ratio, I mean the birth to maturation rate ratio is, the longer it generally takes to reach adulthood. But we can then also have this extrinsic asymmetry, I mean asymmetry imposed by extrinsic factors, which we in this in our terminology relate to the environmental condition. And I mean, I use this example with the resource productivity, where you increase the resource for juvenile, that led actually to ontogenetic asymmetry. You can of course also do it with mortality. In all the examples here we have kept the mortalities stage independent. So the question is, I mean, if we now do a further analysis considering both Z and actually mortality, what is the parameter room for ontogenetic symmetry, unstructured theory, and ontogenetic asymmetry? Well, I mean, this Z, birth to maturation rate ratio, is also interesting because this shows a substantial variation in different groups. So the Z is here the birth mass to mass at maturation. And birth here, I mean, and we can see that almost all organisms, animal organisms, except then birds and mammals, have a very slow ratio. Generally less than, you are born at a mass that is 10% or often 1% of your maturation size. For birds and mammals, it's substantially higher. And here we had to use, we used then for birth mass is not when they are born, because they are born very small, but when they become independent of their parents, that they have to search for their food independently. And that explains why some birds have a higher birth mass than mass at maturation. Because, I mean, it's just before they are fledgling, so they lose some energy. But anyway, I mean, this sets up that it seems like amphibians and, birds and mammals differ from all other groups here. So then it's of course important, what are the effects of a Z? And we were very interested into that, and it turns out it's not that spectacular. Because this shows now two plots here. This plot shows then intake asymmetry through RQ. So here we have ontogenetic symmetry at 1. And on this axis we have this Z, the birth to maturation size ratio. And the light gray area here is the parameter space when we have overcompensation in juveniles. The darker gray when we have overcompensation in adults. Right hatched domain here is when do we have juvenile-driven cycles, and this left hatch is when do we have adult-driven cycles. And what we see from this figure is two major things. One is not very much happen. The body's, this ratio doesn't affect very much except one thing. The most important thing is that the parameter space for ontogenetic symmetry, I would say, is relatively slim. In most of the parameter space, we do have ontogenetic symmetry. The other thing we see is actually that these juvenile-driven cycles, they disappear above a ratio of around 0.3 here. And that can be related to actually that you reduce the time delay, and these type of cycles are really, one aspect of them is actually time delay from juvenile to adult stage. So the only effect that this Z has on anything is basically that high Z values leads to the disappearance of the juvenile-driven cycles. So birds, mammals, again, with respect to overcompensation, there is no real reason to expect that they shouldn't show this also. If we look at the other effect, that is a mortality asymmetry, once again intake asymmetry here 1, we see the same thing basically over most of the parameter space. We have some type of cycle or some type of overcompensation, either in adults or in juveniles. We see that it's asymmetric here because the area then with symmetry appear at a higher intake asymmetry here. But that is then it's coupled then to actually that you have a mortality symmetry in this case. But the general conclusion overwhelming these both pictures is the parameter space for ontogenetic symmetry is very limited. The role is ontogenetic symmetry. So, here is your problem. Present ecological theory actually has a problem, what I call the tightrope walker's dilemma. It's based on a delicate balancing of different rates leading to symmetry. But I mean, as soon as, for example, Q gets larger than 1 or P gets larger than 1, you fall off. And if Q is larger than 1, you fall off in the other direction. So, ontogenetic symmetry, present ecological theory, is, as I argue here, a limiting case then for specific parameters combination. So, to conclude, I've used here then basic energetic relationships at the level of individual and shown how that can give rise to symmetry breaking in ecological systems. I argue then that the concept of ontogenetic symmetry and ontogenetic asymmetry forms actually novel and general organization principle based on which we can develop future ecological theory in general. I also show that our consistent effect then on size or state-specific ingesting capacity Q on both community structure and population dynamics. Things carry over from community to population or the other direction, which is another reflection of a generic theory. Ontogenetic asymmetry can result then from both factors intrinsic to the organism as well as factors extrinsic to the environment. So even if we have this nice balancing of ingestion and Q, etc., but resource production for juveniles and others are different, we still get all the effects of ontogenetic similar system. So posing, including both intrinsic factors and extrinsic factors, make it, in my view, even less likely to end up in ontogenetic symmetry. So, conclusion. The domain of ontogenetic symmetry, hence the domain of unstructured ecological theory, is limited. And ecological unstructured theory can, as I've shown here, also be shown then strictly formally to be a limiting case of a more generic theory. This presentation was pretty short. Anyone who wants to read more about this has the opportunity very soon to read this book. It should be more than enough. It's 560 pages. So, yes. Thank you for your attention.